For a long time, scientists thought atoms were like solid, indivisible billiard balls. But in 1897, J.J. Thomson discovered something shocking, a tiny, negatively charged particle called the electron. This broke the old rules. If you can pull a piece out of an atom, atoms aren't indivisible anymore. There was another puzzle: atoms are electrically neutral overall. If there are negative pieces inside, there must be positive stuff balancing them out. But how are they arranged? Thomson proposed a new mental model, famously called the plum pudding model. If you aren't a fan of 19th century British desserts, think of it like a blueberry muffin. In this model, the atom is a spherical cloud of diffuse, positive charge. That's the cakey part of the muffin. The negative electrons are like the blueberries, embedded randomly throughout the positive dough. Because the positive dough is spread out thinly and evenly, the atom is soft and squishy. This model elegantly explained why atoms are neutral and can emit electrons. But was it true? To test it, scientists decided to shoot tiny, incredibly fast, positively charged bullets, called alpha particles, at a thin sheet of gold atoms. Pause here and predict. If an atom is just soft, diffuse positive dough, what should happen when a fast bullet hits it? You'd expect the bullets to punch straight through, maybe bending just a tiny bit. And at first, that's exactly what happened. Almost all the particles went right through the gold foil. But here comes the surprise. A tiny fraction of the bullets hit the foil and bounced straight back. This was completely impossible under Thomson's model. As the scientist Ernest Rutherford said, it was like firing a 15-inch artillery shell at a piece of tissue paper and having it bounce back and hit you. The soft, spread-out positive dough simply wasn't dense enough to repel a fast-moving bullet. The only way a particle bounces back is if all the positive charge is crammed into a tiny, ultra-dense core, the nucleus. Thomson's plum pudding model was a brilliant stepping stone. It introduced the idea that atoms have internal parts. But it ultimately failed because its positive charge was too spread out, paving the way for the modern nuclear atom.